Hi everyone, Professor Bob Young here, and in this instructional video, we're going to be talking about verifying trigonometric identities, and here are some guidelines we're going to look at to start out. All right, the first guideline would be work with one side of the equation at a time. It's easier to begin with the more complicated side first. Two, look to factor expressions, add fractions, square a binomial, or create a monomial denominator. Look for opportunities to use those fundamental identities, and I have those to the right here. Now, these are the identities I want my students to know by heart as they progress in the course, and we've looked at these in previous videos, and they include the reciprocal identities, quotient identities, Pythagorean cofunction, and the even and odd. Okay. If the first three guidelines don't work, try breaking everything into sines and cosines. And then step 5, don't quit, don't give up. Even paths that lead to a dead end or dead ends may help you down the line. All right, when verifying trig identities, it's useful. It's a useful process if you need to convert a trigonometric expression into a form that is easier to use either algebraically or trigonometrically, or some of you in calculus, if you're going to be differentiating or integrating certain things, it's a lot easier the more basic you can make the identity, and we'll see that as we go along. When you verify an identity, the second bullet, you cannot assume that the two sides of the equation are equal because you're trying to verify they're equal. So you can't like do things across the equal sign. And as a result, when verifying identities, you cannot use operations such as adding the same quantity to each side or cross multiplying and so forth. All right, now what we're going to do next is get into some examples here. So let's look at these to start out with. All right, so example 1 says verify the identity cosine x times cosecant x equals cotangent x. Now this first one, we're going to start out a little bit easy here so y'all will get a good feeling for them here. So we're just going to go ahead, as we said in some of the earlier statements, that we can go ahead and break the cosecant into sines and cosines. So cosecant x would equal 1 over the sine of x. And notice angles can be used, they can be stated with variables such as x over here in the side. They're shown with u's in them. Could be thetas, gammas, alphas, any letter. Okay, so this will give us in the next statement cosine x over sine x, which we have just now verified as the tangent or the cotangent, I'm sorry, of x. So notice I didn't cross the line here. I didn't assume that they were equal to begin with. I wanted to use my identities that we have shown and verified that that is a fact. All right, so for example 2, the tangent of negative x, some negative angle x times the cosine of x will equal the opposite of the sine of x. Now notice over here on your even odd identities, the tangent of some negative angle in this second step will equal the tangent of that angle, okay, multiplied by the cosine of the angle. And then again, let's break this into sines and cosines so we can say tangent x by our quotient identity to the right will equal sine x over cosine x times the cosine of x. And then you can cross cancel, or as I like to say, woo, chop chop the cosines out to leave you with what we are trying to verify. So we can say that's fried, dyed, and verified. All right, these will get a little more difficult as we progress here. So in the third example, we've got secant x minus secant x times sine squared x, and you want to verify this is equal to cosine x. So if you were in a calculus course, would you rather work with all this if you were going to differentiate or integrate that left side of that equation, or just simply cosine x? I think I knew which one I would choose. So let's show that these do indeed verify to give you this, the cosine. So in this one, what you have to see is that you can factor out a common secant x from each of these two terms. So this is what they call the old trigonometric binomial. And what is left is 1 minus sine squared x. All right, now I always tell my students on these Pythagorean identities that when you see sine squares and cosine squares in a problem, or tangent squared and secant squared, or cotangent squared or cosecant squared, that your spider sense ought to be tingling. It ought to be going crazy. All right, so next we're going to say that that's secant x times 1 minus the sine squared x would equal cosine squared x. So again, you can look at this first one over here, sine square u plus cosine square u equals 1, and this might appear three different ways. It might be 1 minus cosine square, 1 minus sine square gives you the other, so be careful on these Pythagorean identities. They will appear in different ways. And then we can break the secant into sines and cosines, rewriting it as 1 over cosine x times cosine squared x, and then you can cross multiply a cosine out or chop it, and you will have this third example verified, as that is what we're trying to show. All right, example 4, continuing. I think I'm going to try to go ahead and break this left side into all sines and cosines here. So again, boy, you have to know those identities to the right. So we're going to say cosine theta times secant theta is 1 over cosine theta all over the cotangent of theta. So in the numerator here, we can see the cosine thetas will cancel. And again, notice I picked different angles and so forth to represent angles. And that will leave you with 1 over the cotangent of theta. And notice 1 over cotangent theta by your quotient or by your reciprocal identities is what you're trying to verify. So there you go. Now again, some students may have broken apart the cotangent into cosine over sine and had 1 over cosine theta over sine theta, and then when you divide 1 by that denominator and take the reciprocal, you'll get sine theta over cosine theta, and again you will get to tangent theta. So there are different avenues depending on which identities you use to get there, but you will get there. All right, for example 5 here, we've got the cosine squared x minus sine squared x, and you want to try to show that this equals 1 minus 2 sine squared x. Now, a lot of times I'll have students go, well, cosine square, sine square, that's 1. Be careful. Do not make up your own identities. The Pythagorean identity is, there's an addition between those, not a subtraction that equals 1. And plus, if this was 1, you wouldn't have it verified anyway. Now, you have to kind of use your noodle here a little bit in order to see that on the left side of this, you got cosine square and sine square, while on the right, you're trying to get everything in terms of sine square. So what I would tell my students in my lecture class here would to be go ahead and take this cosine square using the Pythagorean identity and rewrite it as 1 minus sine squared x. And then bringing down this next one, minus sine squared x, you will see when you collect like terms now, you will have 1 minus 2 sine squared x. And this one wasn't really that difficult to verify if, again, you know your identities. All right, example 6 may be a little bit more interesting here. So what I think I'll do on this one, and again, there are a multitude of ways to do it. I'm going to take this tangent of t and I'm going to rewrite it as sine t over cosine t. And others, you can approach it different ways, plus the cosine t over 1 plus sine t. So I'm just going to rewrite that second fraction. And in the end, I want to show that these two fractions will somehow combine to give me secant t. So whenever I add or subtract fractions, I always tell my students, hey, well, if you're going to put those together somehow, we need a common denominator. So in this case, multiplying the denominators, you'll get the cosine of t times 1 plus sine t. Okay, so we'll put that underneath each fraction. So again, you'll have some algebraic skills tested here in trigonometric form. Now, in order to get this first fraction with this common denominator, I hope everyone sees that we need to multiply numerator and denominator by 1 plus sine t. So I'm going to go ahead and put that. So we'll distribute this sine t through and put that result here in the numerator, and that will give us sine t times 1 is sine t, plus sine t times sine t is sine square t. And then we'll go ahead and look at this one. Well, what does this denominator have that this one's lacking? Well, I'm going to need a cosine t in both numerator and denominator. And remember, as long as you do the same thing to both on fractions, it's a legal move in mathematics. So we'll go ahead here and put cosine t times cosine t, and the numerator of the second fraction will give us cosine squared t, and now we have a common denominator. So let's go ahead and rewrite this as the sine of angle t plus the sine squared of angle t plus the cosine squared of angle t all over the common denominator. And we'll see if we can go from there and figure this out. Okay. Now, Young, how am I supposed to get this to secant t? Well, again, when you see that sine t and cosine squared t, it's like, oop, there it is. You have to know it's there. So this will next, in the next step, give us sine t in the numerator plus 1. So there is your Pythagorean identity, maybe one of the most, if not the most important of all, divided by the cosine of t, and we'll just rewrite this common denominator, over 1 plus sine t. And lo and behold, look, we have something in the numerator and denominator we can cancel out or chop, and that will give us 1 over cosine t. So after going through all of that, notice we are there to verify that this indeed is the secant of t. So notice as we progress, we're getting a little more difficult. All right, now this next example, or these next two, as we get more and more into the video, my students will tell you we just don't do the easy ones in the book. We do the challenging ones as well. So I think you'll find examples 7 and 8 much more challenging. So I want to verify the secant of angle x minus the tangent of angle x squared will equal 1 minus sine of angle x over 1 plus sine of angle x. So what I'm going to do first is I'm going to take and FOIL these on the left. Since I have a binomial squared, it behaves just like it does in algebra. So I'm just going to go ahead and multiply these foiling. So the first two terms will FOIL into secant x times secant x will give me secant squared x. The outside and the inside terms will give me minus 2 times secant x times tangent x, and the last two terms will multiply, oh, I forgot my x there, excuse me, plus tangent squared x. All right, boy, how am I going to get this to look like the right side, Young? This looks like a beast. So again, I'm going to go ahead and break this into sines and cosines. So using my reciprocal identity, secant squared x is 1 over cosine squared x minus 2 times the secant is 1 over cosine x. Tangent is, stretch that out a little bit, sine x over cosine x, plus tangent squared x will equal, by the quotient identity, sine squared x over cosine squared x. And then I'm going to come over here and rewrite this on the right as 1 over cosine squared x minus, in the numerator, 2 sine x over cosine squared x plus sine squared x over cosine squared x. And then I'm going to go ahead and put all of these together. Now, notice, ladies and gentlemen, the common denominator here would be cosine squared, but on the right side, and here's what you have to do when you're doing these, it's like solving a puzzle. Some books will call this solving a puzzle. We've got to get everything in terms of sine x. So if you'll bear with me here, I'm going to rewrite this numerator as sine squared x and put it together, minus 2 sine x plus 1. all over. Now, I'm not going to put cosine square down here. You can beg me and whatever. I'm not doing it. I'm going to go ahead and rewrite the cosine squared x in terms of sine using my Pythagorean identities here as 1 minus sine squared x. Now, the reason I did it again, everything's got to be sines on the right. Notice I've got some creatures that will factor, both a numerator and denominator. The numerator is what's called a trinomial square in algebra, and when you factor it, you'll get sine x. Sorry, there I used a parentheses when I shouldn't have. Sine x minus 1 times sine x minus 1, which if you FOIL the numerator, it will give you the top of the first fraction, over the difference of two perfect squares in the bottom. 1 minus sine squared x would equal 1 plus sine x over 1 minus sine x. So notice here we do have a cancellation. These are called opposites. When you have sine x minus 1 over 1 minus sine x, you can factor out a negative 1 in one of these or the other, but when you cancel, you will get a negative 1, and then multiplying it through the numerator of what's left, notice what we'll get, and I'll go ahead and use the commutative property as well to switch these around. You'll get negative 1 times negative 1 is positive 1. Negative 1 times sine x is minus sine x, all over 1 plus sine x. And then example 7 is verified. All right, continuing the video, these last few examples are so large that I kind of had to get rid of one to put the next one. So we're going to look at example 8 next, which is verify that 1 over 1 plus the cosine of some angle theta plus 1 over 1 minus cosine of theta will give us 2 plus 2 times the cotangent squared of theta. And again, the difficulty level is going up. All right, so what I'm going to do in both of these is I want to go ahead and get a common denominator here in both of these two fractions. So again, I'm just going to multiply the denominators and put 1 plus cosine theta times 1 minus cosine theta in both denominators here, because that would certainly be the common denominator of the left. Okay, and sometimes it takes longer to set these up than it does to do them. And then what we're going to do is, well, what do I need to multiply this first fraction by to get this? And I think everyone would see, well, this one's missing the 1 minus cosine theta, and we can sneak that down here. So that's what we're going to multiply by, 1 minus cosine theta. And the second fraction would be missing the 1 plus cosine theta, both numerator and denominator. Remember to keep them equivalent fractions. Whatever you do to the bottom, you got to do to the top. So here's where we're at. And now I'm just going to go ahead. 1 times this equals 1 minus cosine theta. 1 times this equals 1 plus cosine theta. So what we're going to end up with is 1 minus cosine theta plus 1 plus cosine theta all over 1 plus the cosine of theta times 1 minus the cosine of angle theta. And notice in the numerator, the cosines go out when you collect like terms, and you'll be left with 2 over. And what I think I'm going to do to make this better is to go ahead and multiply these denominator, the 2 in the denominator together. And notice these are conjugate pairs, so all you have to do is multiply the first and the last 2 terms to get 1 minus cosine square theta. Now I know what a lot of you are thinking, how is he going to get to this, to the cotangent squared? Well, and again, it looks easy when I do it, but when you go to do it, you could be like, that's what the early guidelines said, don't give up. You may not get there right away, but you will eventually, if you keep working at it, get there. All right, so next I'm going to use my Pythagorean identity, noticing that, well, that 2 over 1 minus cosine square theta will equal 2 over sine square theta. Now I know a lot of you are going, how is that going to help me here, Young? How am I going to get to cotangent squared? Now don't panic. This is next going to equal 2. Now remember, if there is a sine square theta in the denominator, you can rewrite it in the numerator as cosecant square theta, since they are indeed reciprocal identities. So again, you've got to know your identities in order to manipulate things. And then, something about cosecant squared. Well, that's equal to 1 plus cotangent squared, so I can go ahead next using my Pythagorean identities and replace cosecant square with 1 plus cotangent square theta. And lo and behold, when I distribute this 2 through, I am going to have yet another identity verified. Okay. Okay, so for examples 9 and 10, we're going to go ahead now, and this is not actually copied right. We're going to try to verify that cosine to the 4th power of some angle t minus the sine to the 4th power is going to equal 1. This should be a minus in here, so let me fix that. Sorry about that. We'll make it look good. All right, 1 minus 2 times the sine squared t. Now, what you have to see in example 9 is, again, a lot of your algebra comes back into play. This is the difference of 2 perfect squares. Hopefully, you'll recognize that. And this will factor into cosine squared t plus sine squared t times cosine squared t. That will get you the 4th power back on these, minus sine squared t. Kind of crunched that, didn't I? Now here we go again. Wait a minute, Young. Cosine square plus sine square is the Pythagorean identity 1. And these will just crop up more and more. 1 times anything is itself. So 1 times cosine square t minus sine square t will just give us that. And then I think we saw this in a previous example when we got down here. This was one of the earlier and much easier examples, that if we're after all sine square t's on the right side of the equation, we have to take this cosine square t and rewrite it as 1 minus sine square t, and then bring down the minus sine square t, and then we will have this thing again verified, 1 minus 2 sine square t, and we are down to our last example on this video, example 10. Okay, so for these longer verification examples here, now I'm going to go ahead and FOIL both of the bottom ones here on number 10, cosine theta minus sine theta. Now again, remember, you can take each one of these and write it not once but twice whenever you square a binomial, and you can use your binomial square principles just like you do in algebra here. So this one sometimes intimidates students. Is like, how are you going to show, Young, that these 2 binomial squares are going to equal 2? Oh my gosh, I mean, this is a monstrously, it looks like, long and difficult problem, but I think you will be surprised as we keep going here. So if you FOIL the first 2 binomials or use your binomial square principles, you'll get the first 2 multiply to give you cosine times cosine, cosine square theta. The outside and the inside 2, you'll have cosine times minus sine is minus cosine sine. The inside 2 is minus cosine sine. So you're going to get 2 minus 2 cosine theta sine theta. And then plus, watch your signs, sine square theta. Okay, the second 2, again, foiling or using your binomial properties there, you're going to say plus cosine times cosine is cosine square theta. The outside and the inside 2 terms will FOIL into plus 2 cosine theta times sine theta. You've got positive on both of these, and then plus sine square theta. Now when you collect like terms here, notice, hey, this and this go out when you collect like terms. Plus 2 minus 2 go to 0. You've got 1, 2 cosine square thetas when you collect like terms. You've got, I'll underline like terms different amount of times here, 2 sine square thetas. And lo and behold, if you factor a 2 out of each one of these, you have 2 times cosine square theta plus sine square theta, which is really just saying 2 times 1, and all of that, yes, verifies to 2. Okay, so I hope that was enough examples and explanations and the process of verification that will help you in your studies. Bob Young signing off. Keep up the great work.